This is a video reviewing some basic Lewis structures. We'll just go through a couple of examples. First one we'll do is K2O, which is also known as potassium oxide. Potassium oxide is a unique example because usually when you're doing Lewis structures, you're getting no metals are involved. This one has a metal involved. That's something you want to keep in mind as you're drawing its Lewis structure. So we have two potassiums and one oxygen. Now, one thing you want to remember is when you look at the periodic table, potassium has one free electron that wants to get rid of. Oxygen has 6. It wants to gain 2. So this actually makes sense as a compound because the potassium will get rid of its electron, or these two potassiums will each get rid of their electrons, and then oxygen will have a complete octet. And the reason it works so well is because potassium has another octet right under this electron. So that really fulfills the octet rule for all of these atoms. Oxygen gets 8, potassium's 8 left. So under this one free electron's valence shell, once it loses this one, and same with this one. So this is kind of how you would draw. You could also draw it with just having the oxygen in the middle, the potassium's connected, and then showing the 2 electrons there. They all have complete octets. That's really the main thing to remember. So more common examples, something like CO2 or carbon dioxide. Again, we have 3 atoms involved, so we'll put our carbon in the middle. We'll start with each of the oxygens on the side. So whenever you're drawing Lewis structures, you want to think of how many valence electrons you have to keep track of. Of course, carbon has 4, each oxygen has 6. That gives us a total of 16 valence electrons we got to keep track of. So our final Lewis structure needs to have 16, and the octet rule needs to be fulfilled for each atom in the Lewis structure. So if you were just to start off right away and say, okay, let me just fulfill the octet rule, you can just draw them out like this. And there you see that each atom has 8 electrons. The problem here is that there are 20 electrons in this Lewis structure set. So this is wrong. This is not right at all. The way you would start seeing to find how you would get to 16 electrons is you would start adding bonds. And it turns out that carbon dioxide has 2 double bonds on each side. We want to make a jump from 20 to 16. You have 2 double bonds on each side of the carbon here. Now carbon has its octet rule fulfilled. Now we have to fulfill the octet rule for the oxygens. And now when you look at it, you see that there's 16 total electrons. So that's right. And the octet rule is fulfilled for everyone in the compound. Everybody's happy. The molecular geometry of this guy is called linear because it's just flat, or it's like a line, and it has a bond angle of 180 degrees. Very common example. Another example, SCO2, or selenium dioxide. And as you can see, the dyes are representing how many oxygens you have, oxide being the oxygen. So we'll start with selenium in the middle, just like we did with carbon dioxide, and the oxygens on the ends. So these are all in the same column of the periodic table. They each have 6 valence electrons, meaning we have 18 valence electrons we have to keep track of as we fulfill the octet rule for each of these. So again, if we're going to do exactly what we did before, just fulfill the octet rule, see if that works. Take a look at that. Again, that's 20 electrons. So it must be wrong because we have 20, not 18. We need 18. So go ahead, draw it again. Let's add just 1 bond this time, and then fulfill the octet rule. This time we're just making the jump from 18 or from 20 going down to 18. And we see here we have 18 electrons. That's right. This is the Lewis dot structure here. What's unique about selenium dioxide is that these electrons up here at the top, they push down on the bonds here, giving the molecular structure something we call bent. And the bond angle is less than 180 degrees, it's around 120 degrees, or maybe even less than that, depending on the compound you're dealing with. The last example I'll do is phosphorus trifluoride. Phosphorus trifluoride is a little different from the other ones because we have 4 atoms that we're dealing with. So we'll put phosphorus just in the middle there, and then we'll draw our fluorines. So each fluorine has 7 valence electrons. The phosphorus has only 5. That's a total of 26 valence electrons that we got to keep track of. Just like I did before, first let's just fulfill the octet rule and see if that works. Make sure everybody has 8 electrons around them. So everyone has their octet rule fulfilled. As you can see, this is 26 electrons. So that's it. This is the structure. Just like we saw with selenium dioxide, the electrons at the top here push down on these bonds. And it creates a different shape that we call trigonal pyramidal. Because it's kind of like a pyramid shape. The bond angle comes out to around 107.3 degrees. So it's a very unique molecule.